minus RA times the volume of the reactor. Okay? And then the volume of the reactor, I mean the volume of liquid inside the reactor. Okay? This part on top doesn't count. So it's not actually the volume, it's dependent on how much you fill up the tank. Okay? That's the volume that we use. So you combine these two terms, right? The accumulation plus disappearance is equal to 0, then you get this. So this is an accumulation term, right? The negative sign disappears because you move the accumulation term to the other side, right? So the negative sign disappears, okay? So you have NO0, dFA by dt equals to minus RA times VR, okay? And then you integrate this thing. So if you don't like my math class, you'll come back. You need to integrate again. But I try to keep the integration not so crazy. Okay? So you have NA0 dFA by dt, right? Equal to minus RA times VR. And then you separate the variable, right? You have dFA on the left hand side, you move 1 over NA0 minus RA VR dt to the right hand side. You separate the variables, then you integrate, right? From T1 to T2, from FA1 to FA2. So this assumes that any point in time, right? Oops, sorry, wrong. Has to be dt, sorry, stupid. Okay, so you move dt to the right hand side and you move everything back. dFA divided by minus RA VR and then 1 over NA0. And this looks more like it. And then integrate on both sides from T1 to T2, from FA1 to FA2. What's wrong? No, I'm just curious. Usually when I hear people talk, I want to listen in. Right? It's the nature of me who likes to plug. Okay, so you integrate this, you get T2 minus T1, right? The right hand side, Na0 is constant because Na0 is the number of moles of the reactant A at the beginning. So we pull it out, right? And then you have from FA1 to FA2, then dFA, and then minus RA VR, okay? So this, not an, you should warn me. It's Na on top, because it's on this side. Okay, so this would be the general design equation for the batch reactor, okay? For batch reactor, we focus on time, okay? Because we want to know how long we have to leave the content inside the reactor to achieve a certain conversion, right? So time is the main variable that we want to know, okay? And this one, you see that minus RA and VR is inside the integral, okay? So this one is generic, right? So it includes the case where the temperature changes and case where the volume changes, okay? Temperature can change from the heat of reaction, right? volume change from what? From unequal number of moles on both sides of the reaction, right? And we talk about that, right? We have like V equal to V0 times 1 plus delta A FA, right? Go back to chapter 3, right? That will come back. It will come back. It's related, it's the same course. It's not even a different course, right? Same course. We learn chapter 3 to come back. Always come back to Papa. Huh? Steady state, you can also still have volume change. Right? It depends on the reaction, not the operation. So this volume for isothermal and non-isothermal operations, and then both constant volume or constant pressure. Like, any question? No. So now we get to use this. Should be enough. We have like 18 minutes. Oh, not yet. Okay. So starting from that design equation, if we let T1 be 0, so start at time 0, right? At time 0, there's no conversion, so FA1 is 0. So that design equation becomes something like this, right? T equal to NA0 divided by BR, and integral from 0 to FA. dFA divided by minus RA. Because we pull out the volume, because this one has constant volume. Okay? You still remember the condition where the volume is constant? It's liquid phase or aqueous phase. Volume is assumed to be constant, right? And also gas phase where the number of moles on both sides are equal. So you have constant volume, right? Or when the reactor is rigid and the volume is fixed, that's also a constant volume, right? So if the volume is constant, we can pull out the volume outside of integral, right? And then we have Na0, the number of moles of A at time 0, divided by the volume, which is constant. Mole divided by volume, you get concentration, right? You get concentration. So you have Ca0, integral of 0 to Fa, dFa divided by minus Ra, okay? But sometimes you want the dFa to be dCa, because the rate expression is function of Ca, right? You either convert, for example, R minus Ra is equal to Kca to the n power, right? So to use this integral, you need to write the rate expression in terms of conversion, which is that you need to know Ca equal to Za0, 1 minus Fa, right? And you plug it in here, you get K times Ca0, 1 minus Fa to the n power, right? So this, when you plug this in here, then you integrate, right? So you still need to integrate now. A difficult one I might give you. Simple one you should know, right? Any question on this one? No? Sabay-sabay. And now, I don't think I've finished that example. For constant pressure, okay? Constant pressure means variable volume, right? So we already deal with the variable volume system, right? This is when the reaction is in gas phase and the number of moles on the reactant side and the product side, they're not equal, right? We've seen that in example like nitrogen plus 3 ammonia, and you get nitrogen plus 3 hydrogen, you get 2 ammonia, right? 4 moles on the reactant side, 2 moles on the product side. So this will have some kind of like a change in volume as the reaction proceeds, okay? So with this, we already deal with that. So V is equal to V0, 1 plus delta A FA. Remember this? If you don't remember, go back to your lecture. It's from chapter 3, right? When we deal with this. Delta A is the total mole, right? At FA equal to 1 minus the total mole of at FA equal to 0 divided by the total mole at FA equal to 0. Right? So it could be the total number of moles or total volume. Okay? So you have the volume of the system that changes with time because the conversion changes with time, right? So you put in V0 times 1 plus delta A FA right here. Okay? Then VR0 is the initial volume of the system. Then you can pull this out of the integral. You have NA divided by VR0, moles divided by volume, you get concentration, right? And then you have this thing inside the integral. So the integration will be a little bit more difficult. Because we have a bunch of terms, right? You might need to do partial fraction. What? It's Friday, you should be happy. I need to prepare slides for next week. But then I have free lunch at Somboon today, so I am happy. No, even better, it tastes better when it's free. Yeah. Because we have we have professor from NTU visiting from Taiwan. Yeah, Taiwan. And then they're doing a symposium right now, but then they will have lunch at Somboon. I don't join the symposium, I join lunch. No, because I have to teach you guys, right? The symposium is from 9 to 11. I cannot join, I need to teach you. You come first, you're the first priority. Yeah. Symposium can go, I only go for lunch. Okay, any question? I don't think we have enough time to go through the example. Okay, yep. So we'll do the example on Tuesday. Okay, so to recap today, right? We talked about various type of reactors, right? 4 different type for sure: batch reactor, continuous stir tank reactor, tubular reactor, and semi-batch reactor. Okay. We talk about the advantage and disadvantage of each type so they can choose it more properly, right? Then we start looking at the material and energy balance for reactor design. And then we apply that in case of our batch reactor. We have this design equation right here, okay? For constant volume and constant pressure, okay? So on Tuesday, we'll do an example, right? But Tuesday, we begin with quiz on chapter 6, right? What? I already finished quiz. Yay! So quiz first, then we continue, right? But I also posted homework, right? Homework is like on chapter 6, so catalytic reaction mechanism, right? You can use that as a practice, okay? The homework is due in 1 week, okay? But you just start working on it to practice, okay? homework that I posted this morning.
ไอ้ยา
Yeah. So simple reaction. Okay. Any